What is electron, wave-particle duality in quantum mechanics? Imagine watching a tiny electron move through a slit and suddenly behaving like a wave, creating patterns similar to ripples in water. This strange behavior is at the heart of what we call wave-particle duality. It might sound like science fiction, but it is a real, well-supported idea in quantum physics. Electrons are tiny particles, but they also act like waves depending on how we observe them. When we detect an electron as a small point, it looks like a particle. But when we look at how electrons pass through slits or interact with light, they show wave-like properties. This dual nature was first proven in experiments where electrons created interference patterns, just like waves do. The famous double-slit experiment shows this clearly. When electrons go through to tiny slits one at a time, they still produce a pattern of bright and dark bands on a screen. This pattern can only happen if electrons behave like waves interfering with themselves. The wave aspect of electrons is described mathematically by something called a wave function. This wave function tells us the probability of finding an electron in a certain spot. When we measure or observe the electron, the wave function collapses, and the electron appears at a specific point. Louis de Broglie first suggested that particles like electrons have an associated wavelength, called the de Broglie wavelength. Later, experiments by Davison and Germer confirmed this idea by showing electrons produce diffraction patterns similar to light waves. Understanding this duality is essential for modern technology. It explains how electrons behave in tiny devices and materials used in quantum computers, microscopes, and sensors. These technologies relying on controlling the wave nature of electrons to work effectively. So, in simple terms, electrons are not just particles or waves, they are both at the same time. Their wave-like behavior guides how they move and interfere, while their particle nature shows up when we detect them as individual impacts. This duality is a key part of quantum mechanics and helps us develop new technologies that push the limits of what we can do.